How tall are the high schoolers in Pennsylvania? We actually care about this, by the way. So attached are the heights of 50 high school seniors in a small high school in western Pennsylvania. All right, very small class, seniors. And the weird thing is Pennsylvania appears to measure height in centimeters. I don't know why. We can judge them later, but just make a mental note, okay? So if I'm looking at this dot plot of the heights of the 50 seniors, if I make a guess of the mean of all 50 students, what would you guess the true mean of the heights would be? 170? Okay, so then it says make a guess at the standard deviation. What's the typical distance from the 170 that you observe? 10? So I said? You want to go with 10? We're just guessing. No, we're not going to calculate. We're just guessing. All right? We're just guessing. I know you didn't just say stupid. All right. So now, guess what we get to do? Samples. We're going to take a bunch of samples. Now, instead of trying to guess those heights, so notice the details. We're going to use random.org to select us 5 different students for each sample. Remember, 1 through 50 are the student ID numbers. They're not their heights, right? Average their heights. We're going to average them to whole numbers and put those values here. And you need to do 4 samples of 5. Got it? All right. All right, so we have all of our X bars, remember? So what does each dot represent here? The average of a sample of 5, right? The average from one sample of 5. So we call it an X bar. Remember the symbols. That's a big thing in this chapter. If you miss points in your quiz, it could be because you missed your symbols. So make sure you get those down for your test Friday. X bar means the average from a sample. Okay, so let's talk about our descriptors here of our distribution. What shape do you see? Approximately normal, right? What about the center? Where would you estimate the center being? Around 170, right? Standard deviation is variability. What's the typical distance from the mean on this thing? Did you estimate it? On the previous one, you told me it was 10, right? What'd you say? 5? Typical distance from, if we're saying the mean is 70, what's the typical, on average, what's the distance from 170 these points take on? You think 5? Okay, we'll just do approximately 5. How about that? Make you feel better? Now, compare the 2 dot plots. How are they similar? How are they different? Okay, we said up here, the first dot plot, this one is individuals, right? Okay, maybe I'll just do it down here. How are they similar? How are they different? Okay, number 1 is individuals. Number 2 are samples. Okay, what else? How are they similar? Let's start there. They have the same mean. Anything else they have the same? Shape is the same. So same shape, they're both approximately normal. What about variability? Different, okay, so variability on number 1. Is it big or little? Comparatively, it's bigger. Has bigger variability. And number 2 has smaller or narrower. Okay? So, we went from individuals to samples, and like before, we saw in the previous lesson with the proportions, when you incorporate it being samples instead of individuals, our variability is going to go down, right? Lower variability gives us better estimates of the population. We like that. All right? Here. So the mean of all the x bars, if you do every possible x bar of a distribution, the mean of them is the mu, the true population mean. Sometimes the way they give it to you in a question is the claim. Okay? They claim the average number of hours of sleep is blah, 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 blah. That's the population mean. That's what we claim it is. Okay? Now the variability of the x bars, we noticed that it went way down, right? So you're going to take the population standard deviation, which is given, and you're going to divide it by the square root of my sample size. Again, it's dependent on sample size, right? Bigger sample means I'm dividing by a bigger number, so it's going to get lower. All right. Is it normal? A sampling distribution of a sample mean taken from a normal population is going to be normal in shape. You're like, well, duh. Yeah. So if the population is normal, we saw that that sampling distribution was normal, right? Now we bring this up because when we did proportions, the only way we knew it was normal is if we did large counts test without having to do every possible sample, right? So with means, the conversation shifts a little bit. How do we know if that distribution is going to be normal without doing all the work? Well, there's actually 3 things. The first one is this. If the population was normal, then we know the sampling distribution will be normal. All right, we'll deal with the other options tomorrow. When it comes to z-score, if you're going to do z-scores, it's going to be your sample mean, your x bar, minus mu, the population, divided by the standard deviation over the square root of n. That is on your chart. Yes, there's clinics behind you if you need one. But yeah, help yourself. Alrighty, let's try this out. Every day, people watch 1 billion hours of videos on YouTube. That breaks down to every single person on earth watching YouTube videos for 8.4 minutes per day. For U.S. teens in any given day, the amount of time spent watching YouTube videos is approximately normal, with a mean of 18.5 minutes and a standard deviation of 5.3 minutes. Okay? You good?
Oh, yeah.
Okay. Okay, so I like to shorthand this. So the mean is 18.5. The standard deviation is 5.3. All right. Find the probability that a randomly chosen teen watches YouTube for more than 25 minutes. So it says a randomly chosen U.S. teen. How many people is that?
1.
1. So it's not really a sample, is it? No. So if I want to find this, if you want to put this in context, that's fine. Where's the mean? 18.5, right? It says more than 25. So where would 25 be? Over here on the right. And if it's more than, which way am I shading? To the right, to the right. Thank you very much for that. All right. So now what do? How do we find that probability? Norm CDF. Lower boundary of 25. Upper boundary of big number. What's the mean going to be? 18.5, and sigma will be 5.3. Okay, so let's crank this out, see what we get in our calculators. Okay, I get 0.1100, right? So 11% chance that a randomly chosen teen watches more than 25% or 25 minutes of YouTube a day. Are you above average? Only on Fridays. All right, so that's nothing new. That's like chapter 2 business right there. We did that. Now look at number 2 here, or the next part. Suppose we choose a simple random sample of 10 U.S. teens. So now we're dealing with the sample size, aren't we? Mm-hmm. We know that affects our standard deviation, so we have to embed that in our calculation. X bar is the mean amount of time watching the YouTube videos for the sample. What is the mean of the sampling distribution of X bar? If we took every possible sample of size 10, what would the mean of all the X bars be? It'd be whatever the true mean is, which was 18.5 minutes, right? C says, calculate and interpret the standard deviation of the sampling distribution. So we've got to use that standard deviation equation. It's the population standard deviation divided by the square root of our sample size. So 5.3 divided by the square root of 10. It's 1.68. Then we got to interpret, right? Your favorite part. So when we interpret, we have to talk our sample size. We got to talk about context. What is it we're averaging? We would say the average number of hours watched on YouTube. No, it's not hours, is it? It's minutes. JK, just kidding. I was just seeing if you're paying attention. Minutes watched on YouTube. A sample of 10 teens. That's all context and sample stuff, right? The average number of minutes watched on YouTube for a sample of 10 teens typically varies by 1.68 minutes from the mean of 18.5 minutes. So again, it's the interpreting, I made that up. Interpretations that can eat our lunch sometimes, right? We can do this. If it's an average, it has to be more than one, right? Got to incorporate. All right, now, find the probability that the mean amount of time spent watching YouTube for the teens in the sample, so this is incorporating our sample, exceeds 25 minutes. So it's kind of the same picture, isn't it? This is still the mean. This is still the sample mean. Now it's the sample mean. So what's changing? Only thing changing in my work is the standard deviation, correct? So my lower boundary is 25, upper boundary is big number. Mean is 18.5. Standard deviation is what we calculated, 1.68. This is good. So my calculator says 5.46 e to the negative 5. What the heck? Does that mean there's a probability of 5?
No. It's like
way lower.
0, 0.
That means what? 0.1, 2, 3, 4, 5, 4, 6, right? So we don't put our answers in scientific notation because we're bigger and better than that, right? We realize that we're talking about probabilities here. Probability can't be greater than 1. So don't tell me it's 5. We want to, and you don't necessarily have to do it like this. What you need to communicate to the reader is that you know that that probability is pretty much 0, isn't it? Very, very low chance that you're going to get an average of 25 minutes or higher in a sample of 10 teens. So obviously my probabilities changed quite a bit, right? Probability for one teen was 11%. The probability of a sample of 10 having that average, pretty much nothing. All right? So, sampling distribution sample means super, super similar, right?